Hello children, welcome to the next part of this video. So let us take now the exercise of 9.3 on the basis of the previous result is that the result was triangles on the same base and between the same parallels are equal in area, and in earlier video we have learned that median divides a triangle into two triangles of equal area. So on the basis of these two results, now we have an exercise 9.3. Let us take question number 1 from this exercise, that is exercise number 9.3. Question is, E is any point on the median of a triangle ABC, then show that area of ABE is equal to area of AC and E. So first of all, we draw a figure of this question, that is question number 1. Figure is here ABC is a triangle, and the question is E is any point on median AD of a triangle ABC. So let this AD be the median of this triangle, and we know that median divides a triangle into two triangles of equal area, means area of ABD is equal to area of AC and D. And another information is here, E is any point on the median AD. This is E, it is any point on the median AD. Now what we have to prove, area of ABE is equal to area of AC and D. So we have to find out area of ABE, let us join B to E. Area of ABE is this triangle, is equal to area of a triangle AC and E, this triangle. Now we have to prove that area of ABE triangle is equal to area of ACE triangle. So the given is here in question 1, given is E is any point, E is any point on median AD of triangle A, B and C. Then to prove area of ABE is equal to area of ACE. Now we know that here AD is the median, and by the property of a median, divides a triangle ABD and ACD are in equal areas. So in proof, we can write in triangle ABC. Which one is median here? AD is the median. AD is a median. AD is a median. Therefore, this median AD divides a triangle ABC into two triangles. The two triangles are ABD and ACD, and these two triangles are equal in areas. Therefore, area of triangle ABD is equal to area of a triangle ACD, and call this as equation 1. Now we have AD is the median and E is any point on the median AD. Let us take another triangle, that is this triangle B, E and this triangle B, E, C triangle. If AD is the median, we can say that ED is also median of a triangle BEC, and this BC is the common side of the triangle ABC and EB and C. So if we take in triangle BEC, ED is the median in triangle. Now in triangle this BEC, BEC and triangle CED. We have here, or we can write in triangle BEC, ED is the median here. In triangle BEC, ED is a median. If we have triangle BEC and ED is the median, and we know that this median divides the triangle BEC into two triangles of equal areas. The two triangles is here, BED and CED. Therefore, area of BED is equal to area of CED, because ED is the median of a triangle BEC, and this median ED divides the triangle into two triangles, that is BED and CED. So these two triangles are equal in areas. So name it as equation second. Now, what we have to prove? We have to prove that area of ABE, this part, area of ABE is equal to area of ACE. But we have area of ABD, this ABD, and area of BED. If we subtract area of BED from area of AB and D, so if we subtract BED area, this triangle, from this big triangle ABD, after subtracting that we get the area of ABE is equal to, in this side we have, if we subtract area of CED triangle, this from A, C and D, so we get area of A, C and E. So we can here write subtracting equation second from first. Now subtracting equation second from first, we get area of ABD minus area of BED is equal to area of ACD minus area of CED. Now, if we have area of ABD minus area of BED, this is ABD minus area of BED, so we get area of ABE here. It is area of ABE is equal to, it is area of ACD minus area of CD. ACD is here A, C, D minus area of CED. After subtracting area of CED from ACD, we get area of A, C and E. That equals to area of ACE. This is the result. So area of ABE is equal to area of AC and E. Now the question number 2 is from the same exercise, that is exercise 9.3. Question 2 is, in a triangle ABC, E is the midpoint of the median AD of a triangle ABC. Show that area of BED is equal to 1/4 of area of A, B and C. Exercise 9.3, question 2. So first of all, we draw the figure of this question. A, B, C is a triangle. The statement of the question is AD is the median of this triangle. This one be the median of this triangle. And we know that This median divides the triangle ABC into two triangles of equal areas. That is, area of ABD is equal to area of ACD. And the other information is E is any point on the median AD. This is E. And it is given that E is not here any point, but E is here midpoint of the median AD. So we have to prove that area of, so first of all we join this. If we join this side one. So the given condition is, E is the midpoint of median AD. E is the midpoint of median AD of triangle ABC. Then to prove area of BED triangle, this area of BED is equal to 1/4 of area of the complete triangle, that is A, B and C. ABC triangle. Now here, first of all, in this triangle ABC, we have a median AD here. So proof, in triangle ABC, AD is the median, In triangle ABC, AD is a median, and we know that this median divides the triangle into two triangles of equal area. Therefore, area of triangle ABD, this triangle ABD, is equal to area of a triangle AC and D, ACD. That implies area of triangle ABD is equal to, if this triangle ABD is equal to area of a triangle ACD, then we can say that area of a triangle ABD is equal to half of the area of a triangle A, B and C, because the two parts are equal in areas. So we can say that area of a one part is equal to half of the area of a whole triangle. Now that equals to 1/2 of area of the complete triangle, that is A, B and C, and we call it as equation 1. Now if area of ABD is equal to 1/2 of area of ABC, now let us take another triangle here, A, B and D. Now E is the midpoint of median AD. That means if we join midpoint with the opposite vertex of a triangle, then the line segment is said to be the median. That is, BE is the median of a triangle A, B and D, and this BE median divides the triangle ABD into two triangles of equal areas. So now in triangle ABD, BE is a median. BE is a median, therefore area of triangle ABE or ABE is equal to area of BED, or we can write it as area of BED is equal to 1/2 of area of ABC, because the two triangles is here BED and ABE are equal in area. So we can write area of BED is equal to half of the area of a triangle A, B and D. So area of BED is equal to 1/2 of area of ABD. Now we call it as equation second. What we have to prove here, area of BD. Now in second we have area of BD is equal to 1/4 of area of ABC. 1/4 of area of ABC. But we have it is 1/2 of. It is area of ABD. But in equation first, what is area of ABD? That equals to 1/2 of area of A, B and C. So we here using second in equation 2 we get the result. Using first in second we get area of BED is equal to 1/2 of into area of ABD, but area of ABD is equal to in first 1/2 of area of A, B and C. It is 1/2 of area of A, B, C. That implies area of BED is equal to 1/2 into 1/2 is 1/4 area of A, B and C. So area of a triangle BED, this one is equal to 1/4 of the area of a complete triangle, that is A, B and C. Now let us take another example of the same exercise, that is example number 5. D, E and F are respectively the midpoints of the sides BE, CA and AB of a triangle ABC. First of all, the diagram of this triangle ABC. ABC is a triangle. So we have here D, E and F are the midpoints of BC. So on side BC there is a midpoint DE, there is a midpoint D. And now another side is here, E is the midpoint of CA. This is ECA and let this E be the midpoint of CA and F is the midpoint of AB side. ABC is a triangle. D, E and F are the midpoints on side BC, CA and AB respectively. Then to prove is area of BDEF is a parallelogram. First of all, first part is we have to prove that BDEF is a parallelogram. So for to prove here question 5, to prove first part BDEF is a parallelogram. This is first part. Now second part is, that is area of DEF is equal to 1/4 of area of A, B, C. And the third part is here, area of BDEF, area of BDEF is equal to 1/2 of area of ABC. That is 1/2 of area of ABC. Then prove. Let us take the first one, that is BDEF is a parallelogram. So for this BDEF, if we join this BFE, this one, we know that F and E are the midpoints of two sides of a triangle, that is AB and AC. So in the chapter of quadrilaterals, we have learned the midpoint theorem. That is, if a line segment is drawn through the midpoints of two sides of a triangle, then the line is parallel to the third side, that is FE is parallel to the third side BC, and it is equal to half of the third side. So we use here midpoint theorem. So in proof, in triangle A, B, C, F and E are the midpoints. F and E are the midpoints of AB and AC respectively. Now, if we have a triangle ABC and we have F and E are two midpoints on two sides AB and AC, then we use midpoint theorem. So by midpoint theorem, this FE, this FE is parallel to the third side. The third side is here PC. So we can write FE is parallel to the third side BC, and the same line, that is FE, is equal to half of the third side, that is BC, and FE is equal to half of the third side, that is BC. Or we can write it as, if FE is parallel to the complete line segment, that is BC here, so we can write FE is also parallel to this line segment. So FE is parallel to BD because it is parallel to BC as well, and FE, if FE is equal to 1/2 of BC, and we know that D is the midpoint of this BC, so we can write half of BC is equal to BD. So now FE is parallel to BD and FE is equal to BD. If we join this one, D to E here. Now in this quadrilateral BDEF, we have proved that this FE is parallel to the third side BD, and this same FE is equal to the third side BD. So in any quadrilateral, if opposite sides are equal and parallel, then the quadrilateral is said to be a parallelogram. Therefore, FE is parallel to BD and FE is equal to BD. So we can say that BDEF is a parallelogram. So this one is the proof of first part. BDEF is a parallelogram. Therefore, BDEF is a parallelogram. This is the proof of first part. Because in any quadrilateral, if one pair of opposite sides are equal as well as parallel, then the quadrilateral is said to be a parallelogram. Now the second part is here. Area of DEF is equal to 1/4 of area of ABCD. So if we prove that BDEF is a parallelogram, we have proved it. BDEF is a parallelogram. Similarly, we can prove this. We have proved BDEF is a parallelogram. Similarly, we can prove DCEF is a parallelogram and AFDE is also a parallelogram. So similarly, DCEF and AFDE are parallelograms. Now, second part is DEF is equal to 1/4 of area of ABC. Now, again we take this parallelogram BDEF EF is a parallelogram, and which one is it is diagonal? FD is a diagonal. This one is the diagonal. And we know that diagonal divides a parallelogram into two triangles of equal areas. So the two triangles, this triangle area is equal to area of this triangle. If BDEF is a parallelogram, so we can say that area of DEF is equal to area of BDF. Similarly, DCEF is a parallelogram, then these two triangles are equal in areas, and AFDE is a parallelogram, so the two triangles are equal in areas. That means the four triangles here, AFE, CDE, BDF and DEF are all equal in areas. So area of DEF is equal to area of BDF is equal to area of DCE, that equals to area of AFE. So all the four triangles are equal in areas. So here in parallelogram BDEF, DF is a diagonal. DF is a diagonal, therefore area of BDE or area of BDF is equal to area of DEF, because diagonal divides a parallelogram into two triangles of equal area. So the area of BDF is equal to area of DE and F. Similarly, area of D or DCE is equal to area of DEF. This DCE is equal to area of DEF, and area of AFE is equal to area of DE and F. Area of AFE is equal to area of D, E and F. That means on the basis of the three results, we can say that all the four triangles are equal in areas. Now, area of ABC means this complete triangle is equal to area of DEF is plus area of DCE plus area of AFE plus area of BDF. But all the four triangles are equal in areas, so we can write it as area of ABC is equal to, if all the four are equal in area, we can write it equals to 4 times the area of DEF, or area of DEF is equal to, if we transpose this 4 to the left hand side, we get 1 by 4 of area of ABC. So this triangle DEF is equal to 1/4 of area of a triangle A, B and C. Now the last part of this question is area of BDEF is equal to half of the area of ABC. Now the third part is area of BDEF is equal to 1/2 of area of ABC. 1/2 of area of ABC. But area of DEF is here. BDEF is a parallelogram. That means area of DEF is equal to half of the area of B, D, E and F. So we can write it as, this is area BDF. So this BDF is a parallelogram. That means this FD is a diagonal. This diagonal divides the parallelogram BDEF into two triangles of equal areas. So we can write area of DEF is equal to, or area of DEF is equal to 1/2 of area of BDEF. Now area of DEF is equal to 1/2 of area of this BDEF parallelogram. BDEF parallelogram. Why? Because BDEF is a parallelogram and FD is a diagonal that divides the triangle into two equal areas. So area of this DEF triangle is equal to half of the area of a complete parallelogram BDEF. That implies, so the value of area of DEF is equal to 1/4 of area of ABC. So this, it equals to 1/4 of area of ABC. We have proved in second part. 1/2 of area of ABC is equal to 1/2 area of BDEF, because in second part we proved that area of DF is equal to 1/4 of area of ABC. So in place of area of DF we can use 1/4 of area of ABC. So this 2 will be transposed to the left hand side. We get, it is 2 divided by 4 area of ABC is equal to area of BDEF. So here cancellate, we get 1/2 area of ABC is equal to area of B, D, E and F. We have showed that this area of BDF in third part, area of BDF is equal to 1/2 of area of ABCD, that is equal to 1/2 of area of ABCD. So this is the proof of the third part. Now let us take another example of this same question, that is exercise question number 10. The question number 10 is the diagonal AC and the BD of a trapezium intersect each other at O, and AB is parallel to CD. Then show that area of AOD is equal to area of BOC. Now the diagram of this question number 10 is ABCD is a trapezium. This one be the trapezium. Let it be A, B, C and D. Is a trapezium and it is given that the diagonals intersect at O. So the diagonal AC here and the diagonal BD intersect each other at point O. So we have to show that here area of this AOD is equal to area of BOC. First of all, the given condition is ABCD is a trapezium. Question 10 given ABCD is a trapezium in which AB is parallel to CD and diagonals intersect at O. Now to prove area of AOD, this triangle, area of AOD is equal to area of BOC. Now proof. So here we have two lines here are AB and CD. They are the opposite sides of a trapezium and they are parallel to each other. And AB is parallel to CD. We have two triangles, ABD triangle and ABC triangle. They are on the same base, AB, and between the two parallels, AB and CD. So we know that when two triangles are on the same base and between the two parallels, then they are equal in areas. So area proof triangle ABD and triangle ABC are on the same base the same base is here AB, and between the two parallels are AB and CD. AB and CD. Therefore, area of a triangle ABD is equal to area of triangle A, B and C. Now, in triangle ABD, we have two triangles. It is AOD and AOB. So we can write area of ABD as the sum of area of AOB plus area of AOD. That implies area of this ABD can be written as area of AOB plus area of AOD is equal to. Now this triangle ABC, in this triangle ABC, we have two triangles, that is AOB and BOC. So we can write area of ABC as sum of areas of AOB plus area of BOC. It equals to area of AOB plus area of BOC. Here we have left hand side is area of AOB, and in the right hand side the same area of AOB. So we cancel out area of AOB and area of AOB. The result is here, it implies this area of AOD is equal to area of this BOC, that equals to area of BOC. So in this trapezium ABCD, AB is parallel to CD and the diagonals intersect at O, we have to show that area of AOD, this triangle, is equal to area of BOC. Now we take the triangle ABD and ABC, but the two triangles on the same base AB and lie between the two parallels, then the two triangles are equal in area, but area of ABD can be written as area of AOB plus AOD. Similarly, area of ABC is equal to area of AOB plus area of BOC. Then area of AOB and area of AOB cancel. We get here area of AOD is equal to area of BOC. Now the question number 13 is from the same exercise, that is exercise 9.3. Question 13 is ABCD is a trapezium with AB is parallel to DC and a line parallel to AC intersects AB at X and Y, at X and BC at Y. Then show that area of ADX is equal to area of ACY. So let us draw the figure of this question, that is question number 13. ABCD is a trapezium. This is a trapezium here, A, B, C and D. So ABCD is trapezium, that means AB is parallel to CD, and in the question it is given that a line parallel to AC. So AC is here diagonal. We have to draw a line which is parallel to this diagonal AC, which intersects the line AB at X and BC at Y. So let us draw a line, this one, which is parallel to the diagonal AC intersecting AB at X and BC at Y. This one, Y here. Now, we have to prove that, now given is, first of all, given ABCD is a trapezium, ABCD is a trapezium in which AB is parallel to CD and XY is parallel to the diagonal AC. It is given. Now to prove, we have to show that here area of ADX, area of ADX is equal to area of AC and Y. It is ACY. Now, we have to show that area of A, D and X, this is A, this is D and X. So, we have to join here D and X. This is triangle ADX is equal to area of A, C and Y. This is A, C and Y. So, join this A, Y, and also by construction we construct here join X and C, this line segment, this one. Now proof, clearly we have to show that here this area of ADX is equal to area of ACY. We know that this AB line is parallel to the line CD and the two triangles here A, D and X, this triangle ADX, this ADX and a triangle ACX, this is ADX and AC and X are on the same base, this ACX, this one. They are on the same base, this AX, and between the two parallels AX and DC, because AB is parallel to DC, and we can say that this AX is also parallel to the line segment DC. So we write here triangle ADX and triangle ACX are on the same base, the same base is here this AX, and between the two parallels is here AX and CD, AX and CD. Therefore, the areas of two triangles, that is triangle ADX, is equal to the area of AC, this triangle is ADX, and area of a triangle AC and X. Now, area of ADX is equal to area of ACX because they are on the same base AX and between the two parallels AX and DC. But what we have to prove? We have to prove that area of ADX is equal to ACX. We proved ADX is equal to area of AC and X. Now, consider another pair of triangles here. Take a triangle ACX and a triangle A, C and Y. This ADX, ACX triangle and triangle A, C and X, and now take another triangle A, C and Y. They are on the same base AC, this AC, and they lie between the two parallels. AC is parallel to XY. So we can say that this area of ACX is equal to area of AC and Y because they are on the same base AC and between the two parallels AC and XY. So now we take it as equation 1. Now triangle ACX and triangle ACY are on the same base, are on the same base. What is same base here? Same base is here AC. And between the two parallels is here AC and XY, AC and XY. So we can say that area of this ACX is equal to area of AC and Y. Therefore, area of triangle ACX is equal to area of triangle AC and Y, and call it as equation 2. After comparing first and second, in first equation here we have ADX is equal to ACX, but in equation second ACX is equal to ACY. So from first and second we get area of ADX is equal to area of ACX, but in equation second area of ACX is equal to area of ACY. This is the proof of this condition. So area of ADX is equal to area of ACX. Now question number 14 is in figure is given. AP is parallel to BQ and BQ is parallel to CR. Prove that area of ACQ is equal to area of P, B and R. This is question 14. The figure is given. This is here AP, P, this is B, this is Q, this one is C, and this one is R. So it is given that this AP is parallel to BQ. This AP is parallel to BQ. This is here Q. AP is parallel to BQ and BQ is parallel to CR. That means the three line segment is AB, BQ and CR are parallel to each other. So to prove is area of AQC. This is A here, Q and C. This triangle. We have to show that area of AQC is equal to area of P, B and R. This is P, B and R. Now let us take a quadrilateral that is A, P, Q, B or A, B, Q, P. In this quadrilateral we have AP is parallel to BQ, and clearly in this quadrilateral there are two triangles that is A, B, Q and P, B, Q lie on the same base, that is BQ, and between the two parallels, that is BQ and AP. So when the two triangles on the same base and between the two parallels, then the area of the triangles are equal. So here given is AP is parallel to BQ and BQ is parallel to CR. This is the given condition. Then to prove area of AQC is equal to area of PBR. Now proof. Here triangle ABQ and triangle PBQ. Triangle ABQ and triangle PBQ are on the same base, the same base is here BQ, and between the two parallels is here BQ and AP. So when two triangles are on the same base and between the two parallels, they are equal in areas. Therefore, area of a triangle ABQ is equal to area of a triangle PBQ, and call this as 1. Now take another quadrilateral here, that is B, C, R, Q. This quadrilateral B, C, R and Q. In this quadrilateral, it is given again this BQ is parallel to CR. If we take two triangles here, BQC is a triangle and BQR is another triangle, lie on the same base, that is this BQ, and between the two parallels BQ and CR. So similarly we can write, or we can say that area BQC is equal to area of BQ and R. So triangle, now triangle BQC and triangle BQR are on the same base the same base is here BQ, and between the two parallels is here PQ and CR. Therefore, area of this BQC is equal to area of BQ and R. So area of BQC is equal to area of BQR, BQ and R, and we call this as second one. Now what we have to prove? We have to show that area of AQC. Now AQ and C is here. In this triangle AQC, we have two triangles, that is ABQ and BQC. If we add the area of ABQ and area of BQC, we get area of AQ and C. And similarly, if we add the area of PBQ and BQR, we get the area of P, B and R. So in equation 1 and equation 2, we have ABQ, and in equation 2, the left hand side is BQC. If we add area of ABQ and area of BQC, we get, after adding ABC area and the area of BQC, we get the area of AQC. So adding first and second here. Adding first and second, we get area of this ABQ plus the left hand side of a second one is area of BQC. Area of B, Q and C plus or is equal to here, it is equal to area of PBQ, area of PBQ plus area of BQR. That implies this one is area of ABQ plus area of BQC. We can write area of AQC. It is area of AQC is equal to area of PBQ plus BQR. We can write it as area of P, B and R. Area of P, B, R. Hence the result. So we have here three line segments AP, BQ and CR. They are parallel to each other. First of all, we have to show that this area of AQC is equal to area of BQR. So we take the quadrilateral A, B, QC. In this one we have the two sides AP and BQ parallel to each other. We take two triangles, that is ABQ and PBQ, lie on the same base BQ, and between the two parallels, and we know that the two triangles lie on the same base and between the two parallels are equal in areas. So area of ABQ is equal to area of P, B and Q. In the same way, we take the quadrilateral B, C, R and Q. In this quadrilateral, opposite sides are BQ and CR. They are also parallel to each other and they have two triangles, that is B, Q, C, and a triangle B, Q and R lie on the same base. The same base is here, that is BQ, and between the two parallels. So the area of BQC is equal to area of BQR. After adding the two, we get the area of AQC is equal to area of P, B and R. Now let us take another example from the same exercise, that is example number 15. Diagonals AC and BD of a quadrilateral ABCD intersects at O in such a way that area of AOD is equal to area of BOC. Then prove that ABCD is a trapezium. First of all, we draw the figure of this question, that is question number 15. It is given that diagonal AC and BD of a quadrilateral intersect at O. Draw a quadrilateral like this. Here it is A, B, C and D is a quadrilateral. It is given the diagonals intersect at O. So here the diagonal is here AC one diagonal and other diagonal is BD. They intersect at O. What we have to prove here? ABCD is a trapezium, and we know that in a quadrilateral, if one pair of opposite sides are parallel, then the quadrilateral is said to be a trapezium. So here we have to show that AB is parallel to CD. Now what is given? ABCD is a quadrilateral in which diagonals intersect at O. ABCD is a quadrilateral diagonals intersect at O. Also, there is another one condition given, that is area of AOD is equal to area of BOC. Area of AOD is equal to area of BO and C. Area of AOD, it is given, is equal to area of BOC. This is the given condition. To prove, ABCD is a trapezium. So, ABCD is a trapezium only when this AB is parallel to this line segment CD. Now proof. Here we have two triangles, that is ABD is a triangle and ABC is another triangle, or on the same base, that is AB, but not lie between the two parallels. So here, if we take the triangle A, or we can write it as area of AOD is equal to area of BOC, this triangle. If we add area of AOB, this common triangle, in triangle ABD, we have two triangles, that is AOD and AOB. And in triangle ABC, we have also two triangles, that is AOB and BOC. If we add, these areas are equal, area of AOD is equal to area of BOC. If we add this area of AOB to this triangle and this triangle, we get the area of ABD is also equals to the area of A, B and C. So here proof is area of AOD is equal to area of BOC, it is given. So adding area of this common part, that is AOB, on both sides, we get area of this AOD plus area of AOB is equal to area of BOC plus area of AOB. Area of AOB. Now we have here area of AOD and area of AOB. Look at the figure, this area of AOD and area of AOB. When equals are added to the equals, the whole are equal. Means area of AOD is equal to area of BOC. So we add here the same area of AOB to this triangle and the area of this triangle. So when equals are added to the equals, the whole are equal. That means area of AOD plus area of AOB is equal to area of this ABD is equal to here BOC plus AOB. This BOC plus AOB, we get area of A, B and C. Area of A, B, C. Now we have here two triangles, ABD and ABC. This one, ABD is a triangle and ABC is a triangle. And we know that they are on the same base AB and they are equal in areas. Here we have proved that area of ABD is equal to area of ABC. And we know that by the result that when two triangles are on the same base and having same areas, then they lie between the two parallels. That means ABD and triangle ABC are on the same base, that is AB, and they are equal in areas here, and they lie between the two parallels. That means AB is parallel to CD, and we know that when AB is parallel to CD, they are the opposite pair of a quadrilateral ABCD. So when AB is parallel to CD, then we can say that this quadrilateral ABCD is a trapezium. Now triangle ABD, triangle ABD, this triangle ABD and triangle ABC are on the same base AB. Same base AB, and they are equal in areas so the two triangles ABD and ABC are on the same base and they are equal in areas, therefore they lie between the two parallels, that is AB is parallel to CD. So take this quadrilateral ABCD, we have proved here AB side is parallel to the CD side, so we can say that this quadrilateral ABCD is a trapezium. Hence ABCD is a trapezium. Because in this quadrilateral we proved that it is one pair of opposite sides are parallel. So in any quadrilateral, if one pair of opposite sides are parallel, then the quadrilateral is said to be a trapezium. Thank you very much.